Hello everyone. In this video, we will talk about a new topic, secant method. This part of material is in chapter 6 on the textbook. Secant method is a very famous method to find the root of linear or nonlinear equation. It belongs to the open method. It's very similar to Newton-Raphson, but it's a little bit different. First, let's talk about why this method is called the secant method. Given a curve, for example, you have a function looks like this. A secant line is a line which passes through 2 points of that curve. So this will be a secant line. When you use secant method to find the root of a function, you need to draw a lot of secant lines of this curve. So that's why this method is called the secant method. The secant method is a technique for finding the root of a scalar-valued function f(x) of a single variable x when no information about the derivative exists. The Newton-Raphson method is a very powerful method for finding the root of a scalar-valued function. However, when you use it, it requires the derivative of this function. When the function is very complicated, it's very difficult to find the derivative analytically. So to avoid that problem, the secant method is invented. When you use the secant method, you don't need to know any information about the derivative. Instead, it requires 2 initial guesses about the root. The bisection method and the false position method belong to the bracketing method, and the Newton-Raphson method and secant method both belong to the open method. Although the secant method requires 2 initial guesses about the root, the 2 initial guesses can be both larger than the root or both smaller than the root. So for example, you have a root here. The initial guess x0, x1 can be both smaller than the root or both larger than the root, x0, x1. It's different from the bracketing method. When you use the bracketing method, either the bisection or the false position, you need to have 2 initial guesses, A and B, and A and B have to bracket the root, which means one of them has to be smaller than the root and the other has to be larger than the root. So the problem we want to solve by using secant method is the root finding problem. Given a function of one variable f(x), we want to find a value of r such that fr equals to 0. The assumptions, we assume that the function f(x) is continuous. Because this method doesn't require any information about the derivative, so we don't need to assume anything about the derivative. Initial requirements, we have 2 initial approximations of the root, x0 and x1. It would be useful if we assume that the absolute value of fx0 is larger than the absolute value of fx1, which means that x1 should be a better approximation of the root than x0. If you have 2 approximations about the root, x0 and x1, you don't know which one is x0, which one should be x1, then you need to compare the absolute value of the function at these 2 points. Iteration process. Given the approximations xn minus 1 and xn, how to find the next approximation xn plus 1? Xn plus 1 is defined to be, so let me show you the formula for the secant method. Xn plus 1 equal to xn minus fxn times xn minus 1 minus xn over fxn minus 1 minus fxn. So let me show you how this formula is derived. Remember that when we use the Newton-Raphson method, we get the value of xn plus 1 based on xn by using this formula. Xn plus 1 equals to xn minus fxn over fxn derivative. When we use the secant method, we don't know any information about the derivative, so this term is replaced by the approximation of the derivative. So it's approximated by delta fx over delta x. And this delta fx is the distance between fxn and fxn minus 1. So it's fxn minus fxn minus 1. And the delta x is the distance between xn and xn minus 1. So it's equal to xn minus 1. Alright, so you can plug in this formula back into this equation, then you get the formula for the secant method. So xn plus 1 equal to xn minus fxn over the approximation value of the derivative, which is fxn minus 1 over xn minus 1. So this should be equal to xn minus fxn times xn minus 1 over fxn minus fxn minus 1. So this is how to derive the formula for the secant method. Let me show you the iteration process graphically. If you have a function like this, assume the function looks like this. This is the root, and we have two initial guesses about the root, x0 and x1. So x1 should be a better approximation than x0, so x1 is closer to the root. And then based on the function value at these 2 points, here and here, we can draw a secant line about this curve. So the secant line, which is a straight line passing through 2 points of this curve, will intersect the x-axis at this point. And this point is the next approximation of the root, x2. And then evaluate the value of the function at x2, and then connect the function value at x1 here and x2. So connecting these 2 points, you will find, you will draw another secant line. Okay, so this secant line will intersect with the x-axis at x3, which is the new approximation about the root. And then based on this value, you can find the function value at this point, and then draw another secant line connecting the function value at x2 and x3. So again, the intersection point should be x4, right? So you can see that after several iterations, we get the approximation value x4, which is much better than the initial approximation x0, right? So x4 is much closer to the root than x0. So this is how to do the iteration process for the secant method. In the next video, we will talk about the halting condition, and then I will give you an example about how to use secant method to find the root.